Welcome, my friends. In this video, I begin my discussion of Chapter 7, Introduction to Hypothesis Testing. In this video, I'll be covering Section 7.1 and 7.4, Logic of Hypothesis Testing, and False Positives and False Negatives. The reason why I'm covering 7.4 in this video is because 7.4 gives the definition of a level of significance, which is used in Section 7.2. So I'd like to just get it out of the way and describe it here. Let's start with a motivating example. Suppose that we're playing a game. A bag is claimed to contain an equal number of blue and red colored chips. A random chip is drawn from the bag. If the color is blue, I win. If the color is red, you win. So here's an image to kind of show this relationship. And this is also discussed in the Grand Valley textbook. So there are claimed to be an equal number of blue and red chips in this bag. I'm going to be taking one out. Let's say there were 4 in the bag. That would be 2 blue and 2 red. Then there would be a basically 2 out of 4 chance that I get either blue or red. Suppose further that you doubt my truthfulness and suspect that there are actually more blue chips in the bag than red chips. So my claim that I made to you is that there is an equal number of blue chips and red chips in the bag, and your claim is that the number of blue chips is greater than the number of red chips. Now this chapter is all about hypothesis testing. And with every hypothesis test, there will be 2 competing claims. In this case, we have my claim and your claim, but we have a different way that we typically represent these. In a hypothesis test, we label these as the null hypothesis, H sub 0, and the alternative hypothesis, H sub A, or sometimes H sub 1. So we could say that my claim that the number of blue chips is equal to the number of red chips is the null hypothesis, and the alternative hypothesis is that the number of blue chips is greater than the number of red chips. Suppose the first chip drawn from the bag is blue, which means I win. But this alone is not enough evidence to conclude anything for certain about the contents of the bag. Suppose we play 3 times, and we replace the drawn chip before each game, and I win each of those 3 times. So the first game, I get blue. The second game, I also get blue. And the third game, I get blue. So basically, I have won the game 3 times in a row. So recall our 2 hypotheses. The null hypothesis was that the number of blue chips was equal to the number of red chips, and the alternative was that the number of blue chips is greater than the number of red chips. So now are you starting to doubt my claim that the number of blue chips is equal to the number of red chips? Well, it's certainly possible for me to win 3 times in a row if the null hypothesis was true, but how likely would it be? So we've calculated this here. The result is still possible under the null hypothesis, but it's starting to get a little bit unlikely. There is only a basically 2 out of 4 to the third power is how you would calculate this, or a 12.5% chance of this happening if the null hypothesis is true. So a little bit unlikely, but probably not unlikely enough to discredit the null hypothesis. But let's say we continue, and let's say that I win 10 times in a row. So what is the chance of this happening if I really was telling the truth? If it really was an equal chance of having blue or red chip drawn out of the bag, what's the chance of me winning 10 times in a row? So again, here are our 2 hypotheses. This is still possible under the null hypothesis, but now it's getting to be extremely unlikely. This is a 2 out of 4 or 1/2 to the 10th power chance, which ends up being 0.098% approximately, or a 1 in 1,024 chance of this happening if the null hypothesis is true. So it still could happen if the null hypothesis was true, but it is very unlikely. The chance of observing this result, if I'm telling the truth, is quite small. So you will likely start to doubt my claim and assume that the alternative hypothesis, that the number of blue chips is greater than the number of red chips, is true, or possibly assume that maybe the bag only contains blue chips. Now the probability that we calculated here is going to be what's called a p-value. It's the probability of observing results as extreme or more extreme as your sample, assuming that the null hypothesis is true. So assuming that the number of blue chips is equal to the number of red chips, what's the chance of observing what we observed, or in some cases it makes sense to say something more extreme. In this case, there's really nothing more extreme than me winning every time, right? And in general, a lower p-value is going to give us better evidence for the alternative hypothesis. Note that the p-value is not the probability that the null hypothesis is true. That's not what it's saying. It's saying that if the null hypothesis was true, what's the chance of getting the results that we got? And later we're going to introduce something called a level of significance, which is going to allow us to officially determine whether or not we should reject the null hypothesis or not. So let's summarize some of the information that we have been discussing. Whenever you run a statistical hypothesis test, there's going to be two competing hypotheses. First, we have the null hypothesis, which we denote with a capital H subscript 0. And this typically is going to refer to what we might think of as the default position that a researcher might want to challenge. Or it could be just like a statement that someone has made, or maybe like a claim, right? And typically this is going to relate to a statement of no difference or potentially no relationship between variables, which kind of depending on the type of hypothesis test that you're dealing with, one of these descriptions might make more sense. And then we're going to have an alternative hypothesis that has to be kind of opposite to the null hypothesis, right? And we denote this with a capital H subscript A, or sometimes you might see it with a 1 in some textbooks. And this represents a claim that contradicts the null hypothesis that the researcher would like to try to prove. And this statement typically is going to relate to maybe a difference between variables or maybe representing some sort of relationship between variables, kind of depending on the context. And then what you're going to end up doing is you're going to be gathering a sample to try to see which of these hypotheses seems to be more likely to be true. And based on the results of the sample, you're going to be making one of two what we call decisions. You're either going to not reject the null hypothesis. We usually say fail to reject the null hypothesis. And you're going to be making that decision when the data is relatively consistent with the null hypothesis. So let's say that we played 10 games of that chip drawing game, and let's say I won 6 times, right? Okay, you'd expect that, since it's a 50-50 shot, you'd expect there to be, maybe 5 games on average for me to win. But so if I won 6, that's not really all that inconsistent with the null hypothesis. We probably would not reject it. Or in the other case, you may reject the null hypothesis when the data that you have gathered is very inconsistent with the null hypothesis, such as drawing a blue chip 10 times in a row, right? Oh, that's very, very inconsistent with there being an equal number of red and blue chips, so I'm probably going to reject that claim, right? So it's very important to note here that we're always going to be making our decision by referencing the null hypothesis, because that's kind of like the claim that's up for debate here. And we want to say at the end here whether or not we're able to reject that claim or not reject that claim. A common analogy that's made to hypothesis testing is the courtroom example. So this is just kind of one way to kind of see how some of these terms map onto something that you might be more familiar with. And individuals who are accused of a crime are typically considered to be innocent until they are proven guilty. So if we wanted to kind of map this onto a hypothesis test, we could say, well, the default position here is that the individual is innocent with respect to any crime that they have been accused of. We don't just assume automatically that they're guilty. No, the default position or the null hypothesis is that they are innocent. The alternative hypothesis that the prosecution would like to put forward is that this person is actually guilty of whatever crime they have been accused of, right? And then once we go to court and we have the lawyers kind of go at it with each other, and they're going to put forth evidence, which is kind of equivalent in statistics to like taking a sample, we're going to be making one of two decisions, right? We're either going to not reject the null hypothesis or like not reject their innocence. Basically, we would make this decision if there's not evidence beyond a reasonable doubt, is usually kind of the benchmark here. Then we would fail to reject the null hypothesis. So we could say, well, maybe there's a little bit of evidence against this person. He doesn't have the greatest alibi, but we don't really have, we don't have DNA evidence against this person. We don't have good enough evidence to really say that he's guilty. So we're not going to reject we are going to fail to reject the null hypothesis. We're not going to say that they are guilty. Or it could go the other way. If we have evidence, usually what we say is beyond a reasonable doubt, we're going to reject the null hypothesis and instead conclude the alternative hypothesis. We're going to say, we have the DNA evidence. We have, he has no alibi, and his friend actually, reported him. We have all this evidence against him, so we are going to reject his innocence and say that he actually is guilty of the crime. So just another way to think about some of these terms and how they might map onto something that might be more familiar to you. Okay, next we're kind of going into the 7.4 section here, because now we're going to talk about how your decision may or may not actually comport with the reality of the situation. So let me kind of explain what I mean by that. So when you eventually make a decision, it's either going to be to not reject the null hypothesis, and you would make that decision when you think it's more likely that the null hypothesis is true, or you could be rejecting the null hypothesis when you think it's more likely that the alternative hypothesis is true. But the true hypothesis in reality doesn't necessarily have to comport with your decision. So if the null was true, you could end up rejecting the null hypothesis, or if the alternative was true, you could end up failing to reject the null hypothesis. So sometimes you could be making a mistake, or what we call an error, or in other cases, you might make the correct decision. So the first correct decision would be this first box here. So if the null hypothesis is true, then you should not be rejecting it. This is the case where someone is innocent of a crime and you basically let him go, right? That would be one correct decision. And take a second to think about where the other correct decision would be. So the other correct decision would be if the alternative is true and we reject the null hypothesis in favor of the alternative. That would be our other correct decision. This would be like the person is guilty of the crime and we actually do put them in jail. That would be the other possible correct decision. But then we have these other two quadrants here, which are representing what we call errors, and we number them. So we have the type 1 error, which is when the null hypothesis is true and we reject it. So this is like the person is innocent of the crime, but we end up putting them in jail, which does happen from time to time. And we would call that a type 1 error. Type 1 error is the null is true and we've rejected it. On the other hand, we have what is called the type 2 error, using the Roman numeral 2 here. And this would be when the alternative is true and we fail to reject the null hypothesis. So this is like when the criminal gets away with the crime, right? The alternative is true, he's actually guilty, but we don't have enough evidence to put him in jail, let's say, right? So if the null hypothesis is true, then there's the chance of making this type 1 error. And the probability of making that error, we label that with the Greek letter alpha, which is oftentimes called the level of significance. And this actually happens to be what we're going to be using to determine whether or not we reject a null hypothesis or not when we eventually conduct a hypothesis test. So this is a value that you are typically going to set. And usually the problems that we will do will just tell you, use a level of significance or alpha value of 0.05 or maybe 0.01. And we're only going to be rejecting a null hypothesis if something called the p-value ends up being smaller than this value. But I think a lot of people go through the hypothesis testing and they lose sight of what this number really means. The level of significance is what we call the type 1 error rate. It's the chance of making a type 1 error, the chance of rejecting the null hypothesis when it is true. On the other hand, if the null hypothesis is not true, the alternative is true, then we're actually having the possibility of making not a type 1 error, but now a type 2 error. And we typically use the Greek letter beta to represent this value. And due to technical constraints, it's a little bit more difficult to actually know what the type 2 error rate is. But something that you should know is just that these two errors actually kind of go in an opposite direction. So the lower the alpha value is, the higher the beta value is. So it's kind of almost like a balancing act. So you sometimes want to consider which of these errors is more serious, because in some cases, one error might be more serious than the other. So you might want to set your alpha value to be either higher or lower to kind of account for that. Now, in some cases, a problem might not specifically state the level of significance, and the standard is to use 0.05 if it is not stated. So if a problem doesn't tell you a level of significance, it really should, but if it doesn't, then you're going to be assuming that it's 0.05 or 5%. That's something that we're going to need to eventually make our decision in any hypothesis test. So here is kind of a somewhat comical example, but that maybe you've seen somewhere on the internet. Let's say that our null hypothesis is that someone is not pregnant, and the alternative is that that person is pregnant. And so just take a second to think about what would a type 1 and type 2 error mean based on these hypotheses. Okay, so a type 1 error says that the null hypothesis is true, but we've rejected it. So this person is not pregnant, but we have concluded they are. So that would be this one right here. Type 1 error, sometimes called a false positive. So this person is clearly not pregnant. He's a man, and he's not pregnant, and this doctor is telling him that he is pregnant. So this is rejecting a true null hypothesis or type 1 error. But on the other hand, the type 2 error kind of flips it around. It says the alternative is actually true, but we kind of went with the null hypothesis. So the type 2 error would be this person who is clearly very pregnant here, and the doctor is telling her that she is not pregnant. So this is sometimes called a false negative, or failing to reject a false null hypothesis. So I know that some of the wording can get a little bit kind of confusing here. So what I try to remember in my head is that with a type 1 error, the null hypothesis is true. And with a type 2 error, the alternative is true. So I just kind of start from there, and then I kind of logic from there. So if I know a type 1 error is associated with the null being true, then I know that the error must have meant that we went with the alternative. Or with a type 2 error, if I associate in my head that the alternative is true, then that means the error must mean we went with the null hypothesis, basically. Okay, so here is a problem for you to try. So medical tests that are used to diagnose a disease or sickness are not always 100% accurate. So consider the following hypotheses for an individual who took a COVID-19 test. So let's say the null hypothesis is that the individual does not have COVID-19. And the alternative is that the individual does have COVID-19. And basically the results of the test are going to tell you one or the other. So remember that type 1 error is rejecting a true null hypothesis or a false positive. And a type 2 error is failing to reject a false null hypothesis, or what we might call a false negative. So go ahead and pause the video and see if you can write down and determine what a type 1 and type 2 error might represent in this situation. Okay, so let's go ahead and let's just kind of give an overview of hypothesis testing as it's going to be done. We're going to be doing a whole bunch of different types of hypothesis tests. And the details are going to vary a little bit based on each one, but each one is going to have the same general kind of a framework of steps that we're going to be following. We will eventually be using the Fred technique, which we've used in other videos for confidence intervals, but here's just the general overview of hypothesis testing. So with all hypothesis tests, one of the first things you're going to want to do is set up your null and alternative hypotheses, and then you would go ahead and you would collect a sample, which would just be given in a problem that you're doing in this class. And then you'll always want to use that sample data to find something that is called a test statistic. So the information or the data in the sample could be made up of a lot of different numbers. So you could have, maybe like a table that has, 4, 6, 10 different numbers. And you want to somehow translate all of that information, all of those numbers, into a single number that kind of summarizes the information from that sample. And that's what we call a test statistic. So instead of dealing with all these different numbers, let's summarize it all into one single number, and that's the test statistic. And this is always going to be a value associated with some known distribution. And the distributions we're going to be using in this class are going to be either the z distribution or t distribution, two that you maybe are familiar with, as well as the chi-square distribution or the f distribution. And then from there, once you've calculated this test statistic, there'd be like a formula you'd plug into to find this value. You're going to use that value to find what is called a p-value, which we discussed a little bit earlier. And this is the probability, which represents how likely it is to observe the results in your sample, or more extreme, in favor of the alternative hypothesis, assuming the null hypothesis is true. And I would encourage you to go back to that example with the chips in the bag, because I think it makes more sense when you think about it in the context of an example. But this is the definition here. The main thing to know about the p-value is the lower it is the better evidence in favor of the alternative hypothesis. And that it's not simply the probability that the null is true, but when the p-value is lower, it does suggest that the null is less likely to happen or to be true. And that's what I'm saying right here. The lower the p-value, the better evidence for the alternative. And then depending on how low that p-value is, you're going to either reject or fail to reject the null hypothesis. And what you end up doing is you compare that value to that level of significance. You might remember that's the type 1 error rate. And here is the decision rule that we make in this class. So if the p-value is less than or equal to the level of significance, we're going to be rejecting the null hypothesis. And if the p-value is higher than the level of significance, we're going to fail to reject the null hypothesis. And there's a little saying that kind of can help you to remember this. And the saying goes, if the p-value is low, the null has to go. If the p-value is high, the null will fly. So if the p-value is low, the null has to go means when you have a very low p-value, lower than the level of significance, you're going to be rejecting the null hypothesis. And when the p-value is high, the null will fly. Well, what does that mean? Well, the null will fly means like we're not going to reject it, right? We're not going to reject the null because it's flying, it's good, right? And so when the p-value is high, we would be failing to reject the null hypothesis. So you can use that as a way to kind of remember when to reject or not reject the null hypothesis. Okay, so here is just a brief example of how those things might be kind of applied. So let's say we have this set of hypotheses, which is very similar, and actually we're going to do this example in the next video related to the chi-square test. So let's say that the null hypothesis is that highest education level achieved and employment status are not associated. And the alternative is that highest education level and employment status are associated. So by employment status, I mean like whether or not you have a job or not. And by highest education level, we mean like, did you have a high school education, bachelor's degree, master's degree, et cetera, right? So is there an association between maybe people who have a higher degree are more likely to be employed, or maybe there's not really an association there? So what we would do is actually in this type of problem, you would have a table of information, and from that table, you would have to calculate what is called the test statistic. And it turns out in this case, the test statistic is a chi-square value. And that value, let's just say it's 5.79, right? So you would take this information that you would gather from a sample, you'd plug it into a formula, and that would spit out this value, this what we call a chi-square value of 5.79. And that would be our test statistic. And then from there, you would calculate a p-value. And there's many different ways you can calculate these p-values. For me, we're typically going to be using the TI-84 calculator, but you could also use statistical software. You could use certain probability tables that have been created. But basically, you're going to be using this value that you found, and that will calculate what is called the test statistic. So let's say, that will calculate the p-value. So let's say that we got a p-value of 0.0552. So what does that number mean? Well, that means if the null hypothesis was true, which is if the highest education level and employment status are not associated, then there is only about a 5.52% chance of receiving those results in our sample, or more extreme, or like even more associated, right? So there's only about a 5% chance of that happening. So let's suppose that we are using a type 1 error rate, or level of significance of 0.05. Then what we would do is we would compare our p-value to the level of significance. 0.0552 is greater than 0.05. So then we would remember that saying, if the p-value is high, the null will fly. So we would fail to reject our null hypothesis. And we'd say there's not enough evidence based on this level of significance in our sample to suggest that the highest education level attained and employment status are associated. Okay, so I know a lot of the details are kind of left out here, but I want to give you one kind of overview example here. We'll have a lot more details in the future videos. I just wanted to show you kind of in a nutshell how the hypothesis testing is going to be working. Now, I'll just note here, there is this image in the Grand Valley textbook, and I just wanted to say something a little bit about this in terms of when you should be rejecting a null hypothesis or not, or when you should be even looking at that level of significance. So it turns out that the lowest level of significance that's typically used is 0.01. So if you end up with a p-value that's lower than 0.01, then you don't even really need to reference the level of significance, because it's going to be lower than any commonly used level of significance. So they're saying right here, if your p-value is between 0 and 0.01, then you should just go ahead and reject the null hypothesis. Now, if you're somewhere between 0.01 and 0.1, that's the range of levels of significance that are typically used. So in that level, you're going to want to look directly to the level of significance to make your decision. And only if your p-value is lower would you reject the null hypothesis. And if you have a p-value that's anything larger than 0.1, then that's higher than any traditionally used level of significance, so you don't even really need to reference a level of significance. You can just go ahead and fail to reject your null hypothesis. Okay? I would maybe encourage you to come back to this video after you've watched a couple other of the videos related to hypothesis testing, because I know there are a lot of details that were introduced in this video and maybe not everything made 100% sense. So I think once you've seen a few more examples with hypothesis testing and you've done some more of the details, it could be helpful to come back to this video to kind of understand this stuff a little bit even better. But anyways, that's all I have to talk about in this video. In the next video, we will introduce the chi-square test, and we'll go through a complete example.